Assalamualaikum students, selamat pagi. Okay, so kita masuk ke dalam topik baru. We are going to go into a new topic called sampling. Actually, we've looked at sampling in our earlier lectures where it is used in sampler. Okay, so sampling is basically converting analog signals into discrete time signals or digital signals. So for sampling, we need to use periodic sampling, which means that periodic means that it is a sample is taken at every t seconds. What it means that xn is a product of an analog signal taken at every t seconds, which produces a discrete time signal. So t is a time interval between samples, sela masa antara sampel, also known as sampling period or sample interval. And T is associated with a frequency. So F equals to 1 over T. This is frequency is Fs is sampling rate. Yeah. So Fs is sampling rate or sampling frequency with the unit of Hz. Okay. This is what we have looked into in the earlier lectures, where we see that an analog signal enters a sampler. So at every t second, we see that one sample is taken as the discrete time signal. Okay, so analog signals is given by xat equals to a cos omega t plus theta. Okay, so since since omega equals to 2 pi f, capital F, so we substitute this into the equation, so we get a cos 2 pi f t plus theta. So for discrete time signal, the equation is given by xn, a cos omega n plus theta, and again small omega is 2 pi f. Okay, so substitute that into the equation, so we get a cos 2 pi fn. All right, so the relationship between t, the continuous time, with discrete time n is t equals to n capital T equals to n over fs. All right, so for as I have mentioned earlier, f is the unit is hertz. Okay, so for f and f, the unit is hertz. Okay, and for capital omega and small omega, the unit is radian per second. Okay, now when we want to convert the analog signal into discrete signal, so we simply substitute this persamaan with nt or f over fs, n over fs. Okay, so remember the relationship again. So this is t equals to n capital T equals to n over fs. So simply substitute the t, right? Now, if you look closely, okay, the frequency variables of f at capital F and small f are linearly related. Okay, so f small f is f over fs. You can see here. Okay, so this is basically, all right, if I write here, so this is a cos 2 pi fn. Okay, so f equals to f over fs. Now the same goes for omega equals to capital omega t. Now the range of frequency variables for the continuous time signal is basically negative infinity to infinity. And for discrete time signal or sinusoids is -1/2 to 1/2, and for in radians is -pi to pi. So it completes one cycle. Yeah. Now the highest frequency of a discrete time signal is omega equals 2 pi, or f equals to 1/2. So when we write this, okay, so we see that f max equals to fs over 2 equals to 1/2t, okay, and omega max equals to pi fs equals to pi over t. If we take this persamaan, this equation, okay, we see that f max equals to fs over 2, okay, equals to sampling rate is 2f max. Okay, what does this tell you? Okay, this tells you that the sampling frequency must be 2 times the frequency maximum. What does it mean by frequency maximum? Okay, frequency maximum is when you have a series of no, not a series, a combination of analog signals. Okay, so let's, for instance, okay, you have this signal, okay, so plus another signal at different frequencies. For example, like our voice, yeah. So our voice, we have several frequencies. Actually, it's a combination of several signals. So the highest frequency among of all those signals is f max. Okay, but if you only have one signal, then just one signal lah. But if you have a combination of several signals, you must check the highest frequency among all of the frequencies in that particular signal. So that frequency, the sampling frequency for that combination of signals must be 2f max. Okay, this is what it's called as Nyquist sampling theorem. So increasing the sampling frequency will increase the storage space and processing time. Reducing the sampling frequency will result in aliasing due to overlapping between the desired uh, and it will replicate spectrum of components. What it means that you will create you will create another kind of sorry, not another kind, but signals that you don't really want. So therefore, okay, when you sample, you must make sure that the sampling frequency is at least 2 times the frequency maximum. So the aliasing effect is reduced by this theorem. Okay, so technically uh, it has to be actually higher than 2f max. Okay, means that kalau dalam when you doing your field work and you are taking data and you need to sample, normally we will normally, depending on what type of signal that you want to take, it will be far more than 2 times of the maximum frequency. Okay, analog signals, two different analog signals. We want to sample this signal to become a discrete time signal, and the sampling frequency is 40 Hertz. All right, so how do we change this into discrete time signal? So we look into the relationship between t and n. So the solution is t equals to nf over fs, right? So for x1t, okay, x1t cos 2 pi tan t, okay, to make it become x1n, so we simply substitute t with n over fs, right? So we have here, okay, cos 2 pi tan n over 40. All right, so you cancel this out, so you have cos pi n over 2. So that is your x1n. Okay, right. Now we try to convert or change the x to t. Okay, so x to t, the same method, right? So we write the solution t equals to n over fs. So when you are answering questions, in the test, on the exam, I am expecting that you will do the same or similar way of answering. So solution t equals to n over fs. So you have x 2t equals to cos 2 pi 50t. Okay, simply substitute t with n over fs. So you have x2n over equals to cos 2 pi 50 n over fs. Okay, so you have cos 2 pi 50 n over 40. All right, so here you have cos 5 pi n over 2. Right. Okay, so your answer, so this is x to n. Okay, so you have your discrete time signal. Okay, but look closely at x to n. Okay, for x to n, 5 pi over 5 cos 5 pi over 2n, okay, gives you, it is similar to if you changed it to cos 2 pi n plus pi over 2n. Okay, so this macam mana boleh dapat ni, madam? Okay, so here is the so here you have cos 4 pi 2 plus pi over 2 n. Okay, so ini 5 over 2 5 pi over 2 kan, right? So you boleh you can apa ni, expand this. Okay, so this one you cancel. Okay, so you have 2, so this pi n, so you have 2 pi n plus pi over 2n. Okay, so this is one complete signal, complete cycle. So you can apa ni, neglect that. All right, so this is cos pi over 2n. Okay, right. So here is this is similar to x1n. Okay, similar to x1n. All right. So therefore, dekat sini you see that the x1n cannot be distinguished by x2n, whereas the two signal or the two analog signal in the beginning are two different signals. Okay, so therefore f2, okay, f2 is 50 hertz is an alias of frequency f1 40 hertz at sampling rate 40 samples per second. Okay, so now we have the two signals converted into discrete time signal. Okay, so you see that this is x1n and this is x2n. If you look closely at x2n, okay, we can actually rewrite this. Okay, we can actually rewrite this into 2 pi n plus pi over 2n. Okay, so how this is rewritten? Okay, if you ask, so this is cos 5 pi over 2n equals to cos 4 pi n over 2 plus pi n over 2. Okay, so if we look at this, this is equal to 5 pi n over 2, can? Right, so we simplify this one. This is 2, this is 1. Okay, so we get 2 pi n plus pi n over 2. As you can see here, okay, this is a complete cycle. Okay, so you see that for a signal, for a cosine signal, okay, 2 pi completes one signal again. Okay, so that's why this part you can actually neglect. Okay, alright, so tinggallah pi over 2. This is equal to x1n. Alright, so you have x2n equals to x1n. Right, so two different analog signals gives the same discrete signal. Why? Because aliasing. Okay, because aliasing. So 50 Hertz, this is an alias of the F1 at 10 Hertz at sampling rate of 40 samples per second, or 40 Hertz. Yeah, so means that, okay, your original signal tadi tu, okay, so at 10 this signal, sorry, this x1n, sorry, x1t at 10 Hertz, okay, and x2t at 50 Hertz, when sampled at 40 Hertz, it will give you the same discrete signal. Okay, the reason why is because of the Nyquist. You tak follow Nyquist sampling frequency. Okay, so if you see, right, dekat okay, let's go back. Okay, so here, if we go back to the Nyquist Nyquist theorem, okay, so the Nyquist theorem wants you to sample at f2 max. Okay, f2 max. So means here, okay, so you have here f equals to 10 Hertz. Okay, f1, f2 equals to 50 Hertz. So you are sampling these two frequencies, okay, with the same sampling frequency. Now, if we follow the Nyquist sampling theorem, which is Fs, okay, Fs bigger than or equals to 2f max, okay, obviously for the Fs1, okay, for sampling frequency for F1, signal 1, x1t should is the minimum is 20 Hertz, because 2 times 10 Hertz. Okay, now for the sampling frequency of the second signal x2t, okay, sampling frequency for x2t should be 2 times of the frequency. So 2 times 50 is 100 Hertz. 100 Hertz. Okay, so this will be the correct sampling frequency. Now, as I mentioned before, okay, let's say, okay, you have xt equals to x1t plus x2t. All right, so you have this combination of signals. So we know that for x1t, the sampling frequency must be at least 20 Hertz, and for sampling frequency for x2t is 100 Hertz. Okay. Okay, and then we know that for Fs must be bigger or equal to f max. Okay, so this is the case where if you have a combination of these two signals, which sampling frequency must you use. So because there are two signals here, okay, so the Fs for this case must be the largest sampling frequency, okay, which is 100 Hz. So this applies to the Fmax yang saya bagi tahu tadi. Alright, so when you have a combination of signals, you must look at the highest frequency in that combination, which is x2, alright, and then you have to times that frequency, the signal frequency to 2, then you get your Fs. So in this case, it is bigger or the same as 100 Hz for a combination of both signals. Okay, you understand? Right. So let's look. Okay, so that right. So basically, aliasing can give you different signals. Yeah, and this is an example of aliasing, where what happens in aliasing is that when you have a signal, okay, and it is sampled at different times, okay, at a signal that is sampled at 1 Hertz, okay, 1 Hertz. So you can see that F2, if 1/8 Hertz, you get a slower or a bigger cycle, and for F1 equals to F1 7/8 Hertz, okay, you have a faster signal. So it's taken at different points. Therefore, aliasing happens when you give different the wrong frequency. Yeah? So at but it will take at the same point, but then at different frequencies. So it gives you a signal yang that you don't want, right? Okay, let's look into another example. So consider the analog signal xat equals to 3 cos 100 pi t. Determine the minimum sampling rate required to avoid aliasing. Suppose the signal is sampled at Fs equals to 200 Hz. What is the discrete time signal obtained after sampling? C. Suppose the signal is sampled at Fs equals to 75 Hz. What is the discrete time signal obtained after sampling? And D. What is the frequency f of a sinusoid that yields sample identical to those obtained in part C? Right, so let's do one by one. So for the A, okay, solution A, what is the minimum sampling rate required to avoid aliasing? So to avoid aliasing, we need to know that the Nyquist sampling theorem says that Fs sampling rate must be equal or bigger than 2 Fmax. Okay, so Fmax here is the frequency of the signal. So we need to find what is the frequency of the signal. And so we know that capital omega equals to 2 pi f equals to 100 pi. So this gives you, so we need to find for f. Okay, so f equals to 100 pi over 2 pi, which gives you 50 Hertz. Okay, so that is the frequency of the signal that we get from the equation, the sinusoid. Now, to fulfill the sampling theorem, so we say that Fs must be as equals to 2 Fmax, which is 100 Hertz. Okay, so therefore That is your minimum sampling rate for this particular sinusoid. Okay. Now, question B. Suppose the signal is sampled at fs equals to 200 Hz. What is the discrete time signal? Okay, so the question wants you to change from xt to xn, right? So these fs is given as 200 Hz. So 200 Hz, right? So we know that the relation between t and n is given by t equals to n over fs. Alright, so this is n over 200. So what we need to do is substitute into xat equals to 3 cos 100 pi t. So xn equals to 3 cos 100 pi n over 200. Okay, so then you get 3 cos n, sorry, I'm missing a pi. Yeah. So n pi n over 2. So this is your xn, the discrete signal for xat, right? And if you observe properly, okay, since we get the sampling rate that is to avoid the minimum sampling rate to avoid aliasing is 100 Hz, and the sampling frequency for in question B is 200 Hz, means it is bigger than the sampling the recommended sampling rate, so there should not be any aliasing. Okay, there should not be any aliasing. All right, so for question C, okay, so question C is similar to question B, okay, xt to xn, okay, at sampling frequency equals to 75 Hz. Okay, sampling frequency 75 Hz is much lower than the sampling rate given by Nyquist theorem. Okay, so therefore we expect aliasing. All right. So the same thing that we need to do, we have to write this properly. All your answers should be written properly. The relationship, okay, the relation between t and n is given by t equals to n over fs equals to n over 75. Okay. All right. So this one. So therefore, okay. So substitute. Let's remove this part. Okay, so we substitute. Oops. Substitute into xt. Right. So xat equals to 3 cos 100 pi n over 75. Okay, this gives you this gives you 3 cos 4 over 3 in. Now you look at the side. This can be easily written as 3 cos 6 pi n over 3 minus 2 pi n over 3. Okay, so and then we can simplify this. This is 2. Right, this is, okay, let's move on to this side a little bit. Okay, so we have 3 cos 2 pi n minus 2 pi n over 3. Alright, so again, this is one complete cycle, so we can actually neglect that, and then we can rewrite this as cos 2 pi over 3. Okay, so that is your discrete time signal for this particular for this sampling frequency. Okay, so for question D, okay, I'll just copy and paste this question. Okay, what is the frequency f of a sinusoid that yields sample identical to those obtained in part C? Meaning that the question asks for a analog signal that can give you the identical discrete time signal that we have obtained in part C. Okay, so from the previous from the previous question, okay, so we know that, so from C we know omega equals to 2 pi f equals to 2 pi over 3. Okay, so f equals to 1 over 3. Okay, and then we also know, okay, so because from here we need to find the analog frequency. Okay, so given is f equals to f over capital F over fs, right? So we need to find this f, because this f is the frequency for the sinusoid, right? So f equals to small f times fs equals to 1 over 3 times 75. Okay, this will give you 25 hertz. 25 hertz. Okay, so 25 hertz is your frequency for the new sinusoid. Okay, so we know also that omega equals to 2 pi capital F. Oops, I was too excited there. Okay, so 2 pi F. All right, so here is 2 pi 25 equals to 250 50 pi. So therefore x2t equals to 3 cos 50 pi t. And so this is your sinusoid that is obtained from the same discrete time signal. Okay.